So I think I've got a fun little video for everyone today. We've got some adaptive machining, some polycrystalline ball end mills, some super tiny little carbide end mills, injection molding, acrylic lenses, and analyzing stress concentrations with birefringence. So yeah, let's dig in and see what this is all about. So a little while ago, I picked up a Proto-Ject 150 HP. This is a benchtop injection molding machine designed for small production runs and prototyping work. The machine is very new to me, and I have basically no idea what I'm doing with injection molding. So I don't want to go too much into detail about the machine itself because I just don't have an educated opinion. But I can give you some specs, and we can look at my first project on the machine and what I'd like to do with it in the future. The machine is a combination of pneumatics and hydraulics. This giant cylinder at the top is an air cylinder, which drives a piston to force the molten plastic into the mold. Plastic resin pellets are loaded here in this hopper, and the two temperature controllers up top control the temperature of the barrel, where most of the plastic is kind of sitting waiting to be injected, and the tip of the nozzle. The mold is held in place with this burly 20-ton hydraulic jack, which weighs almost as much as the machine itself, and it's powered by an electric hydraulic pump underneath the table. The machine did come with a test mold, so this is a little spinny top, which I played around with a bunch and shooting black polypropylene and had great fun at it. But I wanted to machine my own mold and start getting a feel for kind of the design parameters of what goes into making an injection mold, because they're surprisingly complex even for a relatively simple shape. I'm a huge optics nerd, and I've always been enamored with the idea of being able to cheaply and easily manufacture optics for just kind of home hobby projects. So I thought machining a double convex singlet lens would be a relatively easy and fun first project. A lens is a very simple shape, basically two spherical surfaces back to back, so there's not a lot of intricate details to worry about, and I can focus on some of the parameters of the molding process itself, like the gate and the runner and injection pressure versus temperature, and worry a little less about the machining of the mold itself. The two halves of the mold are essentially identical. The different spherical surfaces have slightly different radiuses of curvature, but they're basically the same operations for both cases, so I'm only going to show one side. Normally you align two halves of the mold with precision dowel pins. I didn't have any on hand and my McMaster order got delayed, so I'm just machining some locating pins directly into the mold. This is 100% not ideal because they can wear and then you won't have a good alignment, and aluminum's not really a good dowel pin material anyway. But, this is a simple test, so it doesn't particularly matter. So this is just a 2D adaptive, hogging off most of the material to get kind of the rough structure of the spherical surface and the locating pins. The next step is to cut out the spherical profile for the lens, and this is done with that polycrystalline diamond end mill that I mentioned earlier. While relatively expensive, these are actually the cheap import variety, so I got them off eBay for, I don't remember, $30 or $40, I think. This tool is a single cutting edge. The diamond is embedded in basically a matrix, and so it slowly wears away at the matrix, pulling the diamonds off. If I remember correctly, this is a 2mm radius cutting edge, so it's a 4mm diameter end mill, and the shank is solid carbide. Now, why would you use a PCD end mill? Supposedly they give a really nice finish, especially when you're using very, very small stepovers and basically just shaving off small pieces of metal, particularly in aluminum and difficult aluminums that have a high silicon content, like this cast aluminum that I'm milling right now. That being said, I don't know if this will actually make a difference on my machine. I bought it because I wanted to test it out and try it, but I'm guessing a sharp, highly polished end mill designed for aluminum will probably do just as fine of a job on my machine, because the limitation is probably just the chatter inherent in this router and not really the end mill. But it wasn't terribly expensive, and I thought it'd be a fun experiment. And on the upside, assuming I don't just crash this tool and break it, it should last basically indefinitely. PCD end mills wear very, very slowly, and so on a machine that's being run maybe a couple hours a week, I'm never going to dull this tool out. So that's a kind of nice, it might have been slightly more expensive, but assuming I don't break it, it's good for life. After watching my machine go in circles for a couple hours, it was all the little finishing details outside of the main mold cavity. So I used a 1/16 two-flute carbide ball end mill and just did little contour and steep and shallow passes over the gates, the runners, and the vents around the edge. And yes, this is actually the other half of the mold. I, for some reason, lost the footage for the first half. There are perhaps, I don't know, 1,000 important variables to injection molding. I'm pretty sure that's an accurate number based on what I've learned. But of the 1,000 different variables that you need to keep in your head, I've isolated maybe the top 6 or so that seem important for a newbie getting into injection molding like myself. I'm sure this list will change over time as I learn more, but these are kind of my top picks right now. The first one's pretty simple. Clamping force. You really just need enough clamping force to keep your mold shut. And it sounds simple, and it is simple, but it's very important. It's not like machining where you can just go slower or use a lower engagement of the tool. If you don't have enough clamping force, you simply cannot injection mold the part you're wanting to inject without a lot of flashing around the edges. My machine has a 20-ton hydraulic clamp, which is pretty burly for a desktop machine, so I'm not super concerned about this for the type of parts that I'm interested in. The next two are sort of related. Injection pressure and the temperature of the resin both affect how easily or difficult it is to fill the mold. A higher injection pressure makes it easier to fill long, thin, or complicated sections, and kind of the same angle, a higher temperature reduces the viscosity of the resin, which also makes it easier to inject into the difficult parts of your mold. So generally, you want to keep the temperature as low as possible because resins do degrade at higher temperatures and you can get kind of cosmetic defects from elevated temperatures. So the idea is essentially max out the pressure where you can and then start increasing the temperature. But this isn't perfect either because there are also defects that come from overly high injection pressure. So it's a bit of a dance trying to find the right combination. Number 4 on my list is the gate and the runner size, and this kind of encompasses mold design in general, but these seem to be the most critical when getting started. The runner is the sprue section between the nozzle and the main mold cavity, and its job is basically just to get resin from the barrel down into the mold. So you want it to be big enough that resin flows relatively uninhibited, but small enough that you're not wasting a lot of resin. And then the gate is essentially just the very small portion in between the runner and the mold cavity, and you would like this to be as small as possible so you can snap it off easily, but too small and you're introducing a really high pressure kind of bottleneck for all the resin. So again, this is something you have to kind of fiddle with. There's lots of different geometries for the gate and the runner, and I'm not going to get into that because I went with just a very simple design. Finally, the last two are kind of related as well. The resin you choose has distinct impacts on what temperature and injection pressure you work with. Some resins are a lot less viscous than others, so they're easier to shoot at lower pressures or lower temperatures. Some resins don't like high temperatures. Some resins can only be shot at high temperatures. Some resins are always super running no matter what you do. So there's a lot of details about the resin itself. And kind of as a related note, shearing effects are always important with resins, but especially important when working with clear resins. So shearing is when the individual chains of the polymer start to get ripped apart due to high pressures, either from injection or from differential pressures while going around corners or edges, or the difference between the wall of a mold and kind of the interior flow of the resin. So shearing is kind of a complicated subject. And the reason I bring it up is that shearing in clear parts is very noticeable because you can see like actual defects because it's transparent. And this is especially important when you're trying to make a lens because any of those defects or shearing generates kind of stress concentrations, which will totally mess up the optics. Okay, sorry, that was a lot of talking. Let's go shoot some parts on the machine. First, you load the mold up under the nozzle. Press to clamp the mold in place. My model has a pedal, so you just step on it and get your clamping pressure. Pick off any resin that's kind of drooled out of the nozzle, and then you pull the shot. And that's it. You've got a part, hopefully, if you did everything right. The finish right off the machine with that PCD end mill was honestly pretty good. Like, it felt very nice. It was a good smooth finish. You couldn't really catch any edges with your nail. But as you can see here, it's clearly not optical quality. There's kind of this rainbow effect that's happening, presumably from the different almost like vinyl record tracks that the end mill put into the metal. You can see kind of little dips and valleys where there's chatter, presumably. So I wasn't really expecting the pieces that came out of this mold to be, well, very good. So I shot a bunch of tests. I figured I needed to determine temperature and pressure and holding time and kind of all the parameters that I could play with. And I knew I had polypropylene in the barrel already that I had to purge out. So there was going to be some wasted shots anyway. So I just used the first iteration of the mold to dial in parameters. If you can see in the reflections, it's hard since it's clear. Let's see if I can catch the light. There we go. So you can see essentially the machine lines, right? So that's where the ball end mill was doing its circular path, and you can actually see that it was picked up in the plastic, which is pretty impressive, to be honest, because you can't really feel it. There's maybe a feeling of texture to it, but you can't catch a nail on it. So it's a relatively subtle feature, but it shows up really clearly when you look at it. The other interesting thing to note are these white streaks. So you can see it here, and there's streaks here kind of in a V shape. This one has streaks coming here. And the way these always show up are basically coming down as the plastic's being injected. So coming from the runner into the gate, you'll get kind of a radial splaying pattern, and it comes down like so. And so now these streaks, they're called streaks or silver streak or splay. But from what I gather, these are caused by one of a few sources. So it's potentially possible for the injection pressure or temperature to be causing it due to too much shearing action in the polymer or decomposition products inside the resin as it's being injected. But in almost all likelihood for my case, this is just caused by moisture in the acrylic. So acrylic is hygroscopic, which means it absorbs moisture, something like 1 or 2% just sitting at room temperature. And so when you're injecting this at, I believe I was injecting this at 420 degrees Fahrenheit, which is like 150, 180 Celsius. Essentially the water that's been absorbed into and onto the surface of the resin pellets boils, and it causes this streaking as it smears out through the mold. So this showed up on essentially every single piece that I shot to varying degrees. Some of them weren't bad at all. So this one you can see is actually pretty clear. It's hazy because the figure is bad, but there's very little streaking. And so some were good, some were pretty bad, like these. So that was the first run. I tried a bunch of different parameters. Some worked better than others. For the second run, you can see the mold finish is considerably better than it was before. You can actually see reflections now in the surface. So, you know, it's not a bad finish. It is not an optical finish, and I think that's really important to note. First of all, I just polished it up with successive levels of sandpaper, so 320, 400, 600, and then I used some, I believe, 60 micron diamond. And this was all just hand polished, and so that is by no means optical. Like, the figure on this is way off what it should be. You can even see the polishing marks from kind of where I was going with the Dremel and the diamond paste. And so, you know, this is not going to win any awards. The aberrations are going to be terrible, but it is a lot smoother than it was before, and it's really noticeable. I also made a few modifications to the mold. So I enlarged the gate here. So it was pretty small before. From what I gather, acrylic remains relatively viscous even at temperature. And so it probably needed a bigger gate. Originally I did this, I think it was a 60 thou gate, and I ended up just taking a file and essentially widening it on both sides. Next time, you know, lessons learned. Another lesson learned, the runner probably does not need to be this big. It was a 1/4 inch, 0.25. I think that was excessively large for this, so I'm just basically wasting plastic here. So
Next time I'll probably do a smaller gate, or sorry, a smaller runner, maybe have a cold plug to catch kind of a cold slug of plastic that comes out of the front of the nozzle, and then use a larger gate. And we'll see the pieces that I shot are considerably nicer. So this is from the second run. Again, I still was having some issues with full versus partial shots, like this isn't completely full, but some of them turned out actually pretty nice. Let's see, let's find some good ones. Just some splaying it. Yeah, like that one. It's partial, but you can see it actually functions kind of like a lens. And the surface finish is a lot better. See, you can see that the layer lines from the milling are much, much better now that the mold's been polished. So there's still, you know, it's not perfect, and the figure I'm sure is terrible. And there's still a little bit of splay. You can see here some streaking if you look through it. But compared to the other batch, like this one, and I think you can appreciate the difference. So one of the reasons I wanted to do an acrylic lens to start is because acrylic, or really any clear polymer, has an interesting property called birefringence when it's under mechanical stress. And what that means is that the index of refraction of this piece of plastic varies slightly depending on the polarization of light that's hitting it. And this property means you can actually see mechanical stress inside of the lens just by looking at polarized light going through the lens and then looking at it through a polarizing filter. So this is a LCD monitor in the background. It's just showing a white screen. LCD monitors work because of polarized light. So the liquid crystals, the reason they can essentially turn on and off and change their lightness and darkness is because they alter the polarization of the crystal cell, which is then used with fixed polarizers, and that's how essentially an LCD works. So this is spewing out polarized light in a certain direction. It is going through this lens, and as you can see right now, nothing's happening. But if I take a polarizing filter, if we put that in front, you can see something really cool happen. So those light and dark marks are essentially where the polymer inside of the lens are under different mechanical stresses, and so they're refracting the light just slightly differently, which is visible when you look at it through this polarizing filter. So this is a pretty neat property because you can essentially see where all the stress inside of this lens is, right? So it all kind of radiates out from here, which is not surprising because this is where the runner and the gate are. So the polymer is under high stress here as it's squeezing through a very small opening to spread out. And then as it spreads out, you get a more homogeneous, essentially internal stress. And now this is important for a lens made out of polymer because the light that you're seeing through this setup is the same light you would want to be focusing with. And so having different index of refractions in different parts of the lens is bad for a lens because it's not homogeneous. And so this is an interesting way to kind of analyze at a really rough level. There's much more quantitative ways to kind of measure the goodness of a lens, but at least qualitatively you can see how good or bad a particular lens might be. And this is a quick way to help you dial in injection parameters to figure out the best, set of temperature and injection pressures and gate designs to minimize the stress inside of a piece like this. There are different gate geometries, so rather than having just a single tab here, you can have what's called a fan, and the fan helps spread the polymer out more slowly across a wider area, which will lead to less stress. And so that's something I'd like to try in the future. And then I can directly compare that to these and see how it affects things. So if we look at the lens that I did with the original mold before polishing and with a relatively small gate, and compare it to the post-polishing, slightly larger gate, you can see there is a bit of a difference, right? So the side on my right has relatively large stress lines, whereas the one on the left has considerably smaller. They're still present, but quantitatively, they do look smaller, which is quite interesting.
Okay, well, I think that's all I got for you today. Hope you enjoyed that. Like I said, I've got a ton to learn about this machine, so expect more content in the future about mold making or injection molding or DIY optics. And thanks for watching.